Hi, my name is Axel and I'm a PhD student at ARM and Lund University. This is an overview of my paper Deep Ordinal Regression with Label Diversity, co-authored by Magnus Oskarsson and Mark O'Connor. We introduced the concept of label diversity, which generalizes regression via classification for deep learning models. We also provide examples of how this can be implemented in several settings. And finally, we provide some experimental results on a real-world benchmark to highlight the usefulness of label diversity. Regression via classification is a framework for converting a regression problem into a classification problem by discretizing the target variable. Let's assume that we have a dataset with some input variables x, for example RGB images, and some real-valued target variables t. In the direct regression setting, we would try to learn a function that maps the inputs to the outputs directly, for example by minimizing some distance function. In regression via classification, we instead introduce a set of non-overlapping classes on the real line and define a probability distribution over the classes for each target. More specifically, the probability is 1 for the class that overlaps the target and 0 everywhere else. In other words, this is a one-hot encoding of the target. A function can then be learned by maximizing the cross-entropy of the predicted distribution and the encoding. Although regression via classification can be effective, there are several problems with this method. First, it does not exploit ordinal information in the target. A faraway prediction will yield the same loss as a close prediction. Secondly, how to choose the optimal binning of the target. This involves a trade-off between discretization error and the number of training samples per bin. We propose a solution to this problem by introducing multiple sets of overlapping classes. In other words, we are using multiple binnings to create several labels for each training sample, which induces diversity in the target representation. Let's look at some examples of how this can be done in practice. Again, the baseline method uses one set of classes where the bin thresholds are usually placed at equal distance. In the first example, we use the same class width in each set and place them such that they have a constant overlap. Note that this method uses the same number of total classes as the baseline, thus keeping the computational complexity constant. In the second example, we fix the number of classes in each set and then sample the thresholds from a random uniform distribution. Again, we use a one-hot distribution to encode the target for each set. In order to minimize the loss, we need to make correct classification of the target variable for each set, and therefore the loss will be smaller for a prediction that is closer to the true target variable. Label diversity can be used together with any deep neural network by replacing the last fully connected layers and their activations by multiple prediction heads, one for each set. At inference time, we compute the expected value of each distribution to form multiple predictions. The final prediction is computed by averaging the predictions formed by each head. In order to see why this is effective, we can use the ambiguity decomposition to analyze the error of a single prediction. We see that the error is composed of two terms, where the first term is the average of the individual errors and the second term is the variance of the predictions. A non-zero variance is guaranteed due to the different discretization errors in the sets of classes, and hence the final error is guaranteed to be smaller than the average individual error. We test our model on 3 different computer vision tasks, where the first one is age estimation from a single image. We use the UTK dataset, which consists of roughly 10,000 training images depicting persons in the ages between 21 and 60 years old. We use a pre-trained ResNet 50 backbone and then fine-tune the whole network using the Adam optimizer. The table shows the mean average error of the previous state-of-the-art method. Our direct regression baseline shows a slight improvement over this model. We also compare with the regression via classification baseline, where the classes consist of one individual age group. The equal width method improves upon both these models by a small margin, whereas the randomized bins method performs best on this task. We also show improvements on 2 other tasks, historical image dating, where we reach state-of-the-art accuracy, and head pose estimation from a single image. In conclusion, label diversity can be used as a general framework for regression via classification problems, and it consistently improves upon such baselines. In future work, we would also like to investigate whether it is possible to provide any theoretical guarantees for the error reduction. More details are provided in the full paper. Thank you for listening.